All right, good afternoon to everyone. So I think we can start with the last lecture of Brian.
All right, thank you. Good to see you all back. So first, some logistical things. If you go to that link, I've posted an early version of notes for these lectures. It's a bit rough. Hopefully we'll improve them later. If you have comments, I welcome them. But there is at least about 30 references there that will mention some of the things that I've been talking about. Okay, great. Thank you. The other thing is I will talk about some work, so let me just acknowledge that. That's work that will appear very soon, within a week or two, I would say, with Greg Benson and Xiaokai Jian, and that's the supported by various of these big quantum information, quantum gravity groups, including GeoFlow, It from Qubit, and an Air Force, US Air Force program that I'm involved with. Yeah, and it's kind of remarkable that these people fund these things, but that's great. The plan, but we're very grateful, and it's money well spent for anyone out there watching. And I think, hopefully we had last time, we tried to simulate Lenny Susskind. I'll leave it to you whether you need an oracle for that or not. We gave some advice about writing papers, and we talked about complexity in black holes. And in particular, I hope what was clear is that there's a lot of freedom on both sides of this proposed correspondence, but there are some very robust universal features that come out of all the different proposals, like this linear growth of complexity. And so it feels like there is something there, so to speak, even if we don't yet know precisely how to match this particular formula with that particular field theory object. Okay. So today I want to talk about one more topic, which is a little bit more operational, which is that, suppose you did think that the complexity was growing rapidly with time in this specific way, what would that mean in terms of the structure of observables? And that will lead us to the idea of randomness and complexity. And so I'll talk first about randomness and what we sort of mean by that, and what we could hope to achieve. Then I'll introduce this technical notion of K-designs, which are a notion of approximations to the Haar random ensemble of unitaries. And then I'll talk about a particular model, and I'll sort of step you through a calculation, unpublished calculation, that establishes that in this model, you form sort of higher and better approximations to Haar as time progresses in an essentially optimal way. Okay, you can't do better than this. And then at the end, there'll be a little bit of outlook. Okay, we'll wrap up with some, hopefully, thoughts, and then you can all go and have fun in Florence. Okay, so let's talk first about randomness. You've already seen a lot of this in different talks. Jeff, for example, was constantly invoking random unitaries as simple models of black hole dynamics. And we saw it last time as well, which is that if you take some state, psi of t, and this is obtained by time evolving some initial state, psi of 0, that this state tends to equilibrate at long time. And what that means practically, for example, we saw this very explicitly last time, is that the entropies of subsystems of this state look as they would look in an equilibrium state with the same energy density. So even if this microscopically is a pure state, the entropies of any region that has less than half the degrees of freedom will look very close to the entropy of the mixed state of that same energy. So in other words, the purity of this system is being hidden by the randomness, by the sort of scrambling behavior of this unitary transformation. And in particular, in a certain precise sense, the entropies of this state look like the entropies of a random state with the appropriate constraints on energy and so forth. Okay. So what it looks like is that this unitary transformation is effectively generating randomness as a function of time. It's making the state look more and more random. And as far as entanglement entropy is concerned, that randomness seems to reach a sort of maximal value and then stop growing because the entropies saturate, so there's nothing more to say that something's growing larger. But we could ask the question, is there some more fine-grained sense in which the state continues to get more random as time evolves, even past this equilibration time where entropies saturate? And could that increased degree of randomness be correlated with the growth of complexity in some sense? And in fact, that's the basic idea, is that if you have a very random state, it's hard to distinguish that from a truly random state with any kind of computationally bounded calculation. So you just do some finite set of gates. If you have a very random state and some sort of truly random state, how could you tell them apart, right? And indeed, we saw from the point of view of entanglement, it's hard to do that. And today, what we're going to explore is a sort of more precise, but a little bit farther away from black hole setting in which we can establish that. So the idea is, here we see that random-like entanglement lower bounds complexity. For example, you can convince yourself that if I took an arbitrarily large number of qubits and I applied a finite depth circuit to them, I could not generate completely random-like entanglement for all of the subregions. That's just not possible, right? So if you have that random-like entanglement, then you have some guarantee that the complexity is at least more than this finite depth circuit that we saw as a kind of baseline example. But what we'll talk about in this lecture is a way of going way beyond that. That's just a very weak bound that's saying it's not constant depth. Can we really guarantee that the depth actually needs to grow, that the complexity needs to grow with time? Okay. So there's a strong notion, a very strong notion of randomness. Of random, if I say had some, set of unitaries U, this is my set, it's an ensemble. I could equally well consider an ensemble of states like over there. The most random possible structure I could have is if this was Haar random, the Haar ensemble. This is the most random. But at the same time, we know that these Haar ensemble unitaries, I didn't explain this, but it's true that it's very hard to produce these from a finite depth or even small depth circuit. You need to run the circuits that we talked about in the first lecture for a very long time to have a chance of generating truly elements from this ensemble. Okay. But maybe there's a sense in which we could approximate, in some appropriate sense, this ensemble with something more physical and something simpler. So there's two comments here. Comment one is, this is not the only interesting notion. And comment two is we can never get this, can never achieve for a fixed H. So if you have some fixed Hamiltonian, you're never going to achieve this because you have conservation laws. Energy is conserved, the variance of the energy is conserved. So obviously you're not going to get a totally random unitary, right? That doesn't mean such things are not generating a lot of randomness effectively, but this very crude, simple, super strong form of randomness just can't be what's happening there, okay? So that's why point one is important. There are other interesting notions. But what we'll talk about today is, well, okay, we had a conjecture about complexity growth for fixed Hamiltonians, or maybe some ensemble of Hamiltonians, but even ensemble of Hamiltonian is not enough to generate this kind of ensemble. So what we can do is change the problem. Let's say modify the problem. By including time-dependent randomness. So, for example, we could take a Hamiltonian and replace it with the Hamiltonian plus some random coupling with a single extra perturbation. So like imagine taking a Hamiltonian, adding some perturbing operator, but make the coupling of that perturbing operator a function of time. And let this be a random function of time. For example, at every moment in time, it could be a Gaussian random variable, and it's uncorrelated between different moments in time. That would be called a white noise random variable. We could write it this way. We could say that the expected value of this object at different times, and here I'm using math BBE to denote average over the ensemble, not quantum average. This could be something like some strength G times the delta function in time. So just imagine you have lots of little increments, they're all decoupled from each other, and each of them has a Gaussian variable. So this kind of ensemble of evolutions does at least have the right number of sort of freedoms to potentially realize this ensemble. And I'll comment on this case at the end, but what we're going to do is an even more extreme change. We're going to replace the whole Hamiltonian with a sum of purely random terms like this. So just take H and replace it with some H of C of T, and you have a lot of these different couplings indexed by alpha. So just make the whole Hamiltonian totally random in space and time, and that's kind of the simplest possible setting where we could hope to generate something like this very strong form of randomness. And I'll give you an explicit example of this in a second. But you know, we're losing energy conservation, but in many other ways, we retain interesting features of the problem. For example, every instance of the evolution is still perfectly unitary. We still have entanglement growth. We still have OTOCs that grow exponentially with time if you define the model in the right way. So a lot of the features that you find in ADS-CFT can still be embedded in models of this type, but we don't have energy conservation. That's the main thing that we're losing. Okay? Yeah.
Question. Is there any rigorous sense in which we could trade random time dependence by time-independent random couplings? The second example that you gave, right?
This here?
The third one, I guess.
This one.
Yeah. So is there any, yeah, let's pick them to be these couplings to be random, but not time-dependent. Is there a way to relate the two?
You can relate them, and actually you'll see a little bit later on, there are some quantities we're going to calculate which are just not equal to what they should be if you're only averaging over time-independent randomness. Does that make sense? So, that's still a very random thing, and I'm sure for all practical purposes, it will scramble up information, you'll never figure it out. But if you want this very strong notion, it won't be enough. Okay? Any other questions? So the goal of this lecture is to analyze this problem, to actually show that you can effectively reproduce this very strong kind of randomness, and then see what that can teach us about the larger questions we've been thinking about. Okay, so let me talk now about K-designs. The question we need to ask ourselves is, what do we mean by approximating the Haar ensemble? And there's different answers you can give to this question. But one answer is, so the question is, what does approximating Haar mean? And so one answer, not the only one perhaps, but is it means reproducing moments of the distribution. So what does a moment mean? It means that we can consider a very general object, pick a U, and then consider a tensor product of a bunch of copies of U and U dagger. Like this. So it's like you pick one element from your ensemble and you have a bunch of copies of it, right? So it's the same U on every copy, and it's the same U dagger here. And there's K of these, and K of these. And so for any expression of this type, if you average this over U's drawn from the Haar measure, you'll get a certain answer. And we say that an ensemble of unitaries is a K design if averaging over that ensemble gives the same answer as the Haar answer. Right? So let me just write it here. So here's the definition. Ensemble E is a K design if the expected value of this thing is equal to the Haar answer. Okay, so hopefully the definition is clear. Why would we care about this? Well, I'll give you a couple of reasons why this particular notion is nice. Well, among other things, it captures efficiently the notion of otox and scrambling. So if you think about an out-of-time order correlator, it has 2 forward evolutions and 2 backward evolutions. So 2 copies of U and 2 copies of U dagger for the physical Hamiltonian. And so if you wanted to say that the result of your OTOC calculation was as if you had a random unitary, that would mean that this would need to reproduce the Haar value for k equals 2. Right? So it would have some statement about the behavior of out-of-time order correlators, and the statement would be that your dynamics is effectively Haar-like randomness for the purpose of answering these scrambling questions if it's a 2 design, right? And similarly, maybe you care not about OTOX but higher point out-of-time order correlators, then you might need you need more and more copies of U and U dagger. So that also suggests interest in more powers of U. You might be interested in Renyi entropies, right? In that case, again, you would need bunches of copies of the state, right? And you want to average that over your dynamics or whatever. And so again, you might care about these moments of K. And of course, mathematically, if you have enough control over these objects, then you can also just establish some properties, concentration of measure, that sort of thing about the physics of your system that will tell you very precisely that it's close to Haar in some sense. Okay, yeah.
Excuse me, I'm wondering if we start with, let's say, 1 design or 2 design, does it also imply that it's also a higher K design?
Good question. It goes the other way. So a K design is always like a K minus 1 design and on down, because you just trace out some of the degrees of freedom. That's always free. But yeah, generally being a 1 design or 2 design does not go up. So as a famous example, Clifford circuits form a 1, 2, and I think 3 design, but not a 4 design, right? And so these objects are sort of known to exist, but it's not easy to construct them. And what we're going to say is that with a certain physical-ish time evolution, we can actually form K designs, or more properly approximate K designs, as time evolves. So the longer you evolve in time, the higher the value of K that you've effectively reached. And so in this sense, you're doing better and better and better as time progresses of approximating higher and higher moments of the hardest. Other questions? Okay. I want to mention, this is not going to be something that makes a lot of sense, but I just want to flash the words in front of you so you've seen them before. We won't be able to guarantee that some physical system, or let me just put one other reason why I care.
So a quick question. So is there like a reason that you want like a model where like as time goes on you like are able to approximate higher and higher moments, like just from a physics standpoint?
Is there a reason why I want a model? Well, let me put it this way. I expect sorry, who asked the question? Sorry, I was writing, I didn't see.
Okay.
Yeah, so I expect physically reasonable Hamiltonians, like you have in the real world, to have a sense in which they have more and more randomness as time goes on.
Yeah.
So I think there's some notion of randomness growth that just is true in nature.
Okay.
And so what we're doing is we're going to have a model where we can prove a strong statement. That model won't quite be like the kind of Hamiltonian in the center model, because it has this time dependence in it. But it might point the way towards, you know, a way of weakening these statements or seeing some version of them in more physical Hamiltonians.
So like if you take K to go towards infinity, like do you,
Yeah.
yes, like do you get close? So like is the intuition that like as you take K to be larger and larger, you'll get closer and closer to the Haar distribution?
That's right.
Okay.
Yeah. And in particular, you know, like if, for example, if K is large enough, then it guarantees that all these unitaries produce entanglement entropies that are nearly maximal. And then, as I forgot but should have mentioned, another important thing is that K designs give you a lower bound on complexity. So you can't form one of these designs unless you have a sufficiently complex ensemble. There's a question here in the front.
Is a 2 to the n design on n qubits by definition Haar random?
Is a 2 to the, sorry, 2
Yeah,
to
so
the
is
2
there some exponential number? Is there some k design at which it's Haar random? Where you're like, I guess this is a question of if you get all the moments right.
Oh, yeah. Yeah, that should be true just because, yeah, I think that's right.
That's right, okay. Also, there's a question there.
But it's doubly exponent, like it's 2 to the, it's the dimension squared, not just the dimension.
It's doubly exponential, or it's
No, it's
the
not,
dimension
I don't
squared?
think it's,
It's 2 to the 2 times n, is that what you're saying?
yeah, I think so.
Okay,
But
okay.
yeah,
Okay.
don't quote me on that.
Okay.
Can we also quantify, so the question is, can we also quantify closeness to a K design? Yes, great question, we can, and we'll do that right now. So, what about approximate K designs? So I'll just say some words and kind of give you the flavor, but won't really explain too much. So there's something called a moment superoperator, which is the expected value over, using this ensemble of u, x, u dagger. So this is a quantum channel that takes some operator on the k-fold copy of the Hilbert space, some linear operator, and outputs another linear operator. And this is just a repackaging of that object where we kind of flip the U daggers and turn them into operators again instead of like a state-like object. And a suitable notion of approximate K design is that m epsilon as a channel minus m har in a certain norm called the diamond norm is less than epsilon. So I won't define this norm in detail. The important thing to know is that it's a norm that has to do with distinguishability. So it says the following thing. Imagine you have these channels, so someone can like give you the channel, can give you access to the channel, and what you can do is pass an arbitrary quantum state into that channel, including a state tangled with some other system, and then you can make whatever measurement you like on that combined object, and the task is to tell these two things apart. You can't do that better than probability 1 plus epsilon over 2, essentially. That's the meaning of this statement. So if this is very close, then they are essentially indistinguishable in any single shot setting. Yeah, Nima has a question.
So from the physics perspective, isn't it nicer if we defined some measure of randomness or some other pseudo-random measure that said, measurements that take a short amount of time are not going to be able to distinguish the distribution from har?
Yes.
This is like the number of copies. I was always confused about how would we interpret this operationally.
Yeah, I mean, so Nima's questions about operational interpretation or other sensible notions. I'll say, first of all, this is a very strong notion of approximation. It kind of covers all your bases very thoroughly. You might have other questions. For example, suppose I give you more copies, but I only allow computationally bounded adversary. So here I'm allowing arbitrary measurement, including exponentially complex measurement, right? And so that's a really stringent criterion. So physically, I agree with you, like probably those more constrained notions are maybe more appropriate and interesting to understand, but they're harder to say things about. And maybe what's sort of remarkable is that we can actually get this in a pretty reasonable model. In fact, we can make it so that epsilon is exponentially small the number of qubits. So that's like a super strong notion of approximation, and it means that for anything you could ever do in your life, it's equivalent to a K design. Okay? But one thing we do need to do is this object is not a physics object. It's an information theory object. I don't know how to calculate this quantity sort of for a nice model in a simple way. So what we do need to do to make some technical progress is to replace this with something more physics amenable. And that will lead to the idea of frame potential. Let's talk about frame potential. And at this point, I should mention that this kind of approach, especially involving the frame potential, was something that Benny Yoshida and Dan Roberts really pioneered in the black hole context. Here's the definition of the frame potential. It depends on some ensemble and this index k. It's an expectation over the ensemble twice of the trace v dagger u to the 2k expected. So v and u just to parse the expression, are two separate instances drawn independently from the ensemble E. Then what we do is we put them together like this, take the trace, raise it to the 2kth power, and take the expected value over all the elements. Right? So again, you see this flavor. There's sort of k copies of U and k copies of U dagger. The value for the Haar ensemble is k factorial, so it's just a nice number. And this is actually a lower bound, so any other ensemble has larger than or equal to this value. And you might imagine, and it's true, that if you have an ensemble that has the same value as the Haar ensemble, then it's a K design. Okay. More importantly, there's also a bound. This is related to, let's say the frame potential is related to a 2 norm. And that 2 norm is related to the diamond norm via some very expensive, costly dimension factor expression. But you do have a bound, which is that m minus m Haar like that. So this D is the dimension of the total Hilbert space of a single copy. So if we can get this close enough, I mean really close, then you will have a bound on this thing. Okay? And, I don't know, as you stare at these sort of things more and more, you'll start to realize this is the kind of thing you can calculate. Powers of U and U dagger with traces and averages. That's the kind of thing that we could, for example, develop a path integral expression, whereas this norm quantity is much harder to deal with. Okay, so what's the goal? Let's summarize what we've said. We've said that one thing that we could ask for is an ensemble of unitaries that approximates the Haar ensemble as you go on in time. And the notion of approximation that we'd like is this very strong notion, because why not? And that notion can be related to a more physically accessible quantity, or at least computationally accessible quantity. By computation, I mean like with your fingers or a computer, classical computer. This is something we could actually try to calculate. And if we have enough control over this, then we would conclude that we have this strong randomness property. So prove a good approximate K design in some, let's say, random circuit model. And in particular, what we're going to want is that after a time t, we have a K of order t design. This is about the best that you can hope to do. And as discussed in the notes, there is work in this direction. So in the quantum information community, people like to analyze chains quite a bit. That's a very natural setting. And in that setting, the most recent result is by Jonas Haferkamp, in which, I forget, is it the 1/5 power? But essentially, you get something like K design after t of order k to some power. So you need to go, it's not linear, you need to like kind of go longer than k to guarantee a k design, right? This is for what's called a brickwork random circuit. Where you apply layers of gates like this. There's also work by Hunter Jones and collaborators in which they talk about if you make the local dimension large, so you make this a unitary acting on some q-dit instead of qubit, where q is the local dimension, then you can get k of order t. And then this author was also involved in another very recent work that got a lot of attention, where they proved some exact version of this, where it's sort of like a, roughly speaking, it's like a dimension counting argument. You're showing that the dimension of the space generated by these random circuits is growing in a linear way for a very long time. Okay, so there is work here, and essentially what we're going to do is have another model where we get sort of a little bit better relationship between time and k without this large Q assumption. Okay. So let me write the model down without further ado. It's a model that Nima knows well. Yeah.
Oh.
How is a Q scale with 10 or something? Right, the Q is 2 or 3, it doesn't do anything. Right?
Yeah. This is an analysis where you take Q large and like fixed size, I think.
Fixed size? It
Yeah.
doesn't go with.
I mean, I don't want to. They have many statements there, but yeah, it's usually like. For example, one thing you can do that Nick pioneered is mapping to a statistical mechanics model and then solving that model at large Q. So like a Q state POS model where you solve it at large Q, something like that, right? But there's a question about, yeah, whether you're taking the thermodynamic limit or the large Q limit first, and this kind of thing matters.
Oh, Brian?
Yes?
Sorry to take you back. I was just wondering, like, do you have any intuition for the frame potential? Like, it seems like it's minimal for the Haar distribution.
Yeah.
But why? Yeah, is there any intuition for like the form of it?
Is there any intuition for the form of it? There is, yes. In the following, we'll say a little bit more about this actually, but it's a good question. So the reason why you get this k factorial here is because if you look at that moment channel that I wrote down, that has some eigenoperators that are preserved by the application of the channel. So the identity is one of them. But also any permutation is also an identity operator because you're just moving the u's around, and so you still get everything cancels and you just get a unit value. Okay. So there's k factorial dimensional space of eigenoperators with unit eigenvalue. And this object here is also sort of sensitive to that. Basically, it kind of pairing them up in various ways. And this k factorial you're getting is actually going to be counting essentially those zero modes. So we'll see it kind of explicitly, but it's essentially an object that at very long time counts the zero modes of some object. And that's why it's a useful thing. That's one reason why it's a useful thing to think about.
Okay.
Okay. Other questions? So the model, as I promised. There are lots of models for which this analysis will work, but let me just give you one. It's a Hamiltonian which is time dependent. It's an ensemble of Hamiltonians with the following structure. Like this. So I just choose all possible pairs of poly operators on n qubits. And each of these couplings is a white noise random variable. So as promised, I just take my whole Hamiltonian and replace it with totally random terms. Right? So the expected value of any j is equal to 0, and the expected value of j squared is something like j over n delta t. Let me write it this way. The indices need to be the same, otherwise the correlation is 0. So it's like every possible pairwise interaction of qubits, each of them with a random term. Of course, this is just one thing. You could consider higher powers. You could consider fermions instead of bosons. We've done all that. It'll be in our paper. But anyways, this is a model that's usually called a Brownian circuit model. I think it first appeared in this context in a paper that was in the early days of scrambling, called Towards the Fast Scrambling Conjecture. A lot of distinguished authors in that paper. And we're going to analyze this model. Okay, and the crucial thing which lets us do this is that the frame potential in this model is calculable. In fact, it's calculable, well, certain values of k are completely calculable, and otherwise we can get nice bounds on it. So let's see how that works. The crucial thing is that if I have any expression of this form, this is what I need to study, where I have k copies of some fixed operator O with a random coupling, and then k copies of the same thing now with the dagger instead of the original. And here I'm using U star instead of U dagger, but because I'm taking a trace, it doesn't actually matter. So I can either consider U star or U dagger, and U star is more convenient because they all occur at the same moment of time. So I simply need to calculate this expression where, think of C as one of these J things, right? And I'm looking at some infinitesimal time slice, and I'm going to do the calculation for every single term in my effective Hamiltonian. And the answer here is very simple. So if you want to look in the notes, there's a nicer expression, but this is the structure of it. It's the exponential of some variance factor, which sets the overall scale, and then a sum of terms where O sub r refers to an operator O in replica R of the forward directions, and O r bar refers to operator R in replica R bar in the backward directions. So R and R bar both run from 1 to k. We have this subtraction. It's minus sign because you have the relative sign here of minus and plus. And they all appear together in quadrature because, inside the square, because it's all the same random variable in every term, right? So the important thing is you sum everything up first, then you square it, and the overall size is set by the variance of your thingamabob. Okay? And now in the notes there's some exercises. One of them is to reproduce this. Another is to show that the frame potential can be written as follows. In this case, so the Brownian Fk, well, there's a crucial point, which is that this trace V dagger U, where this is for time t and that's for time t, can be replaced with a trace of U to the 2t. This is because all the couplings have 0 mean, and they're all white noise correlated, so there's no correlation between different moments of time. So we could equally well think of 2 copies, 2 independently drawn elements from the ensemble of length t. We could think of that just as well as 1 element with length 2t. So we don't actually need to have this 2 copies, we just double the time and compute an average like that. So what we need to compute is the trace of u 2t, u 2t, u star 2t, u star 2t. And now averaged over, sorry, this is averaged over elements and take the trace. Okay. So all we really did is we took those 2k copies of trace v dagger u, we wrote them all out. Half of them have u, half of them have u star, and we use this little trick to replace v dagger u with the u time evolution for twice as long. So we get this simple object, and then you can show that this is equal to the trace of e to the minus 2t h effective, where h effective is the sum following object. It looks crazy, but let me just write it down. So essentially for every term in our Hamiltonian, we have this calculation for every term and every time step. The ultimate processing of all that together is that we can think about the frame potential as essentially the statistical mechanics of this Hamiltonian, where the temperature, or the inverse temperature, is 2t. And the Hamiltonian is this particular object where we sum over every possible interaction term with this certain combination of the terms in the Hamiltonian on the forward replicas and the backwards replicas. And there's an overall 1 over n, which we chose so that this Hamiltonian has an extensive energy as a function of n. So I don't imagine that you followed in detail that calculation. It took, it takes a little while. But with this basic formula here, if you process that object enough, you can reach it, and there's a fairly careful discussion in the notes. The crucial point is that we boiled down this dynamics problem into an equilibrium problem where we need to analyze the structure of this Hamiltonian. Okay, so what's the structure of H effective? Well, let's start with k equals 1. So there's only one forward and one backward replica. You can convince yourself in that case that this H effective looks like the following thing. I guess there's no 2 anymore. So all I did was I specialized this Hamiltonian to the case where k is equal to 1. So there's just one r and one r bar. And I use the fact that these operators square to 1. So you can expand it out like this. And you have a term which looks like this combination for every pair of polys. So every I and j and every alpha beta. And now the cool thing is there's a lot of structure here. First of all, this model has a ground state with exactly 0 energy. and that's given by the infinite temperature thermal field double between copy 1 and copy 1 bar. So it has a ground state, which I'll write this way. And why is it a ground state? Well, as Chris showed you the other day, when you have this thing, you can push operators through from one side to the other. So this operator here, which is on system 1 bar, can be pushed through that thermal field double, can be pushed through those bell pairs to give you the same operator on copy 1, but with an extra transpose or complex conjugate. It's equivalent because it's unitary. So whenever you act this term on that state here, you can push for each term, push this operator from 1 bar to 1, then it just squares with itself to give you 1, and that cancels with this one to give you 0. So in the jargon, we would say this is a frustration-free Hamiltonian, where every term can be simultaneously satisfied on the ground state. The ground state is unique. It's just this single pairing between 1 and 1 bar. And moreover, I won't go through the details, it's in the notes, but you can also establish that above this ground state, there is an energy gap of order 12J. So this is the ground state. There are excitations above that ground state where you apply Pauli operators to one side of this state. Excitations have the form a Pauli string on copy 1 applied to this state. This has the right number of states because how many Pauli strings are there? There's 2 to the 2n. There's 2 copies of my system, each of which has dimension 2 to the n. And so this is actually a complete basis for the 2-copy Hilbert space. And the really remarkable thing you can show is that for this Hamiltonian, each of these, for every Pauli string, is an exact eigenstate. So we actually diagonalize the entire Hamiltonian for k equals 1. We know the whole spectrum. And in fact, the spectrum is approximately additive. And moreover, above this single ground state, there's a gap of order 12J. Now, I won't, bore you with the analysis of this for general K. I'll just say there's 2 important points. This is just a technical thing you have to go through. For general K, there are K factorial exact ground states. They look like this: infinity 1, 1 bar, infinity k bar, plus permutations. So in other words, we can pair 1 with 1 bar, 2 with 2 bar, like we did for k equals 1, or we can pair them in any permuted way. So we can pair 1 with 2 bar and 2 with 1 bar. And the number of such permutations, we always have to pair a forward with a backward. That's the rule. But we can choose any pairing we like. And so there's k factorial ground states. They're all exact ground states. In fact, that's the dimension until k is of order the dimension of the Hilbert space. Then something else happens, but I won't talk about that. And moreover, there's a gap, which is again of order 12J. So excitations are also of this type. You pick a pairing. That's kind of like your base state. It spontaneously breaks the permutation symmetry amongst the copies. And then you create excitations on top of that pairing. And all those excitations have an energy gap 12J, at least. In fact, they're dilute in a certain precise sense, and we wrote down a path integral which calculates this quantity for any k, and it's exactly what you expect. That's discussed in the notes. So this is actually enough. This is all we need. Let me show you why. Let's bound this partition function. So remember we wanted fk. Well, okay, it's the sum over all the states of my k copy statistical mechanics problem. I know that I have k factorial states with no energy. right? So some of the terms, there are k factorial states with that energy 0. So e to the minus 2t times 0. And there's a bunch of other states, but I know all of those states, I didn't prove this to you, but I claim it's true, that all those states have energy at least 12J. So therefore, we can write this as an extremely crude bound let me write it this way just to make it very explicit. Minus 2t times 12J. So this is a positive, that's a sum of positive terms, the Hamiltonian. These are the zero energy states, and every other state has energy at least 12J. So I'm making a upper bound because in fact the partition function will be smaller than this, since some of the states have energy much bigger than 12J. But this is an upper bound. And so you can see then that fk minus k factorial is less than or equal to d to the 2k times e to the minus 24 jt. Okay? So what does that mean? Well, d is big, right? It's 2 to the n. But e to the minus t is small. And if I make t big enough, in particular if I make it of order n, then I can guarantee that even this factor here in front is overwhelmed. You may recall that I also had a dimension factor when I went to the diamond norm bound, but I can overcome that as well by, again, making t small enough. So I can put these things together and say that m minus m har and so in particular, if I take t to be sufficiently scaling with n, in particular if I take (24jt) to be greater than 4k n log 2 plus 2 over log 1 over epsilon, like this. If I have that large of time, then I guarantee that I form an epsilon approximate K design in this very strong diamond norm sense. Right? So in other words, I had enough control over that quantum channel, the moment map quantum channel, or essentially equivalently over this frame potential. The fact that I had this constant independent of n and k bound on the gap of my effective stat mech problem meant that I could get this very strong result at the end of the day that with time scaling linearly with k, I get an epsilon approximate k design. And in particular, even if I want this epsilon to be very, very small, even if I want it to be, say, itself 1 over d to the 2k, that's a similar scaling with k and n. So suppose you take epsilon to be 1 over d to the 2k, then you need something like 24jt is bigger than 4kn log 2 plus 2 plus another 4kn log 2. But importantly, they scale as k and n. Okay. So let's pause. What did we learn? We learned that for this model of dynamics, this Brownian circuit model, we can calculate the frame potential, or at least we can write a nice expression for it as a stat mech problem. That stat mech problem is not totally solvable, but it's solvable enough that we can count the ground states and bound the gap to excited states. And that information alone is sufficient to give us this very strong result on the approach to randomness. Right? So essentially, the zero energy states are what you would have for Haar, And this gap means that everything else decays away really rapidly. So all the non-har stuff vanishes fast as time evolves, and that's why you have this strong bound on the time to K design. And as I mentioned before, you can show in various senses of the notion of complexity that this kind of bound is sufficient to guarantee that the complexity of ensemble is at least K. And that means the complexity of ensemble here is at least T. So we actually, for this model, established that for this ensemble of evolutions, complexity grows linearly with time. Okay? So this is not an ADS-CFT Hamiltonian, but we didn't have to jump through too many hoops to get a very, very strong notion of randomness and a strong guarantee of this linear complexity growth. This is discussed in a very nice way in detail. Another paper that Nick Hunter-Jones and others were involved with, including Brandau, Preskill, Wissam was on that paper. Yeah, many people, called Models of Quantum Complexity Growth. It's in the notes again, so you can look it up there. So we achieved our goal. We took something that's, discernible as vaguely related to ADS-CFT, fast scrambling, etc. And we were able to show that for this modified problem, you actually do have linear complexity growth. And maybe even more interestingly, you have this very strong notion of randomness that comes out. Yeah.
It seems like you're saying that you have a time scale by which pure state become approximately thermal. Does that have anything to do with scrambling time?
Sure. I mean,
because
this sort of statement means that they're like very strongly thermal, if you like. For this circuit, thermal just means looks like maximally mixed state. And so this means that for any observable involving K copies of the density matrix, it would look like perfectly thermal after a time linear in K.
So to begin with, did you expect this time to be linear in N?
I think it's reasonable to expect a linear time in the following sense, that maybe you need essentially at least a scrambling time for every additional copy that you want to have to be effectively random. Like basically each copy, you scramble it and you get a new random sample. So I think the linear in scaling with K is reasonable. The scaling with N, you could wonder if you could do a little bit better. Like maybe we could improve the factor, or maybe it's even log N, but I think probably log is too strong for this very stringent notion of like this diamond norm with exponentially close error, but maybe some weaker notion. For example, there's something called a tensor product expander, which is like a much weaker notion of like being close to a K design, and for that notion, you would approach this K copy tensor product expander much more rapidly, like where we'd have a better guarantee. So yeah, I think the linear scaling with K is reasonable. It's like every copy is a new scrambling time, at least. And the scaling with N is something that we could quibble about a little bit, but yeah. Okay. All right, so let's step back from technical stuff and yeah.
Why you think you can change N? This is a log S, right? It's the fast scrambler. And because you have like a 2 local sigma.
Yeah.
So you can't probably make it faster than that, right?
I guess if you fix epsilon here, just let epsilon be whatever it is, you might imagine that you could achieve this in time like K log N instead of K times N, because log N is the scrambling time for this object, but I'm not sure if that's actually achievable. And well, let's say the frame potential definitely is not that close after that time, because we can just calculate it. And it only, let's say, like, I wrote it somewhere. So this is what FK looks like. If you calculate it, say, with this path integral approach, or you calculate the partition function more carefully. So there's higher order terms in the exponent, but this is the leading behavior. So it approaches k factorial like this thing going to 0, which is like log n. But depending on how close you want it to be to k factorial, you get these powers of n, not just log n, but n after some period of time. So I think it's kind of a question of what level of closeness you want, and this kind of thing. Okay. Oh, another question.
So there's a distinction between the time it takes to prepare a K design and the time that entanglement saturates.
Yeah.
So by entanglement we mean von Neumann, bipartite entanglement. Is it imaginable that we could define multipartite measures of entanglement that will continue, will fill in the gap from saturation of entropy all the way to things like K design or pseudo-randomness?
Yeah, maybe. I mean, so for example, I guess who was on this paper? Nick, maybe Jordan Kotler, Nick Hunter Jones, Jordan, and I forget the third author. Anyways, I think it's actually in the notes, but they considered like fluctuations of entropies and related quantities at very late time. And they show that there is some like specific structure of fluctuations that only dies out at super long times. And so, yeah, I think there could be some like more subtle structure there, but I don't have anything like insightful to say about that. So, other questions? Okay, so let's actually go back to the original motivation, which was ADS-CFT. And let's consider this situation where we take the Hamiltonian of ADS-CFT and we add to it a perturbation like this. You can calculate the frame potential for this problem as well. You find that Fk is trace m dagger m, where m is e to the minus I t h tilde, and h tilde looks like this. Sum over r So now we have a fixed Hamiltonian. The frame potential is still sort of like something like a partition function sort of object, but now it's more like a real-time object, but for a Hamiltonian it has an imaginary part. So it's like non-Hermitian quantum mechanics, where you have a bunch of copies of the physical Hamiltonian and also some decay term here, which gives your states a lifetime. So they decay away, effectively. What you can show is that this Hamiltonian has k factorial dark states, meaning states that don't decay, at least. That's, again, the k factorial in our Haar ensemble. And if you take a simple model of this H, like suppose H is a random matrix, then you can estimate the size of the decay rates, and you can show that they're all sizable. So except for these dark states, everything else has a finite decay rate of order g. And so you would have a similar kind of bound, actually, that says that if you wait a time such that g times t is long, you would again come close to this very strong form of randomness. So what we physically say is if you take the ADS-CFT Hamiltonian and you add arbitrary random shock waves to the problem, that it's roughly going to actually reproduce this Haar situation. Now that's not quite right for two reasons. First is that this heats the system, it adds energy. So you can't actually focus on a certain band of energies, at least if you make this O simple. So this only really makes sense if you say convert to some Hamiltonian with a finite dimensional Hilbert space and talk about infinite temperature. And then you would have a statement like, you take your fixed Hamiltonian, you add this little bit of randomness to it, and it still generates a K design. And there I would say the story is sort of like quantum chaos of that Hamiltonian is turning into this very strong form of randomness. It's like a machine that converts classical randomness in the form of these random numbers into this very strong form of quantum randomness. Right? And, you can analyze, say, the structure of this Hamiltonian if you assume, for example, that the energy eigenstates of the unperturbed object obey ETH, right? Then you can calculate matrix elements of this, and at least in perturbation theory, say, convince yourself that there is indeed a gap in the decay rates. So this is kind of exciting to me because it's like a connection. Quantum chaos is this somewhat nebulous notion. Is it OTOX? Is it decay of ordinary correlators? Is it random matrix level spacings? Is it complexity growth? What's going on? And this is one more connection between some structure of H and some other notion of generating randomness or generating complexity. Now, another notion that's come up quite a bit in the questions is the idea, is there a question?
Hello.
Hey.
It's a bit naive, but with this model and this random Xi, I was wondering the randomness, or let's say the chaos that we are getting as the output, how much of that is because of these random couplings that we are putting, and how much quantumness is there? Is there some classification not classification, but can we recognize the quantum part of it?
Yeah, it's a good question. So what's quantum about this? So these are just random numbers. If you imagine in a lab, you're just turning you assign your graduate student to turn a dial randomly based on the coins they flipped or what the weather looks like that day. And for each of those dial turns, you apply this operator in a certain amount, right? So that's just a totally classical random process. And what it's outputting for you, if this is correct, is a very strong form of quantum randomness. So quantum states or unitaries that are strongly random in this very strong sort of diamond norm sense. There's no way to distinguish them from essentially a fully random object if you have access to a finite number of copies of that procedure. Yeah.
Yeah, so is the result that this, with H being the ADS-CFT Hamiltonian, you actually do get an approximate K design?
Yeah, I would say for ADS-CFT, it doesn't quite work in the sense that we don't have an obvious set of states to focus on. We keep moving the Hilbert space to higher and higher energy because we keep heating it up. So what you can do is, say, switch to something like SYK or a spin chain, where there's a finite dimensional Hilbert space and a maximum energy. And then for that, and you're looking at all the energy eigenstates, all the states, then we didn't prove this the same level that we proved the previous statement, but in perturbation theory, for example, you can calculate the properties of this. And what you find is that there are K factorial states that don't decay, and every other state decays by an order 1 amount. So this would be similar to our frame potential calculation for the Brownian model, where most of the things that are not this special permutations decay rapidly away, and that decay is fast enough, independent of K and N, so that we would get a strong result.
Okay, so this construction looks similar to this construction by Vazirani, Pfefferman, and
Yes.
Boland, and so I was wondering if it is actually kind of the same, and if you're actually just showing, so they show that adding these random shocks give you pseudo-randomness. Yeah, so are you actually just showing that their construction actually gives you information theoretic randomness?
Yeah, good question. So let me answer after I explain what this is to everyone. Indeed, Boland, Pfefferman, they gave this nice discussion. I mean, so pseudorandomness has entered other places, but this is the most recent discussion, I would say. They gave this nice, well, evidence, let's say, that a simpler version of this, where we do the same kind of thing as here, except maybe this discrete, so we only do it every once in a while, and we only apply a small number of them, so we don't let the number grow with n in time. That even if you do that, it's not information theoretically secure, but it's computationally secure, meaning that no simple computation can tell these states apart. And there, it worked, or at least, I mean, let's say they conjectured that it worked even with a relatively small number of these insertions so that you would not have this information theoretic guarantee. You'd only have a computational guarantee. So if you like, what we're saying is if you simplified the problem and let yourself work at infinite temperature in the right kind of Hamiltonian, then you would have an information theoretic guarantee at long time. And presumably, for such a situation, you'd also have the pseudo-randomness, but that's much harder to prove. Okay. So we kind of think that this is true. So the idea here is that even short time, relatively short time, evolution under the H plus this object, which is the Hamiltonian plus shocks, that you still get this sort of a strong notion of computationally secure randomness. Isaac Kim, John Preskill, Eugene Tang also discussed such related notions, strong kinds of quantum error correction.
Excuse me?
And yeah.
Just a short question. I mean, is it some kind of extension of my last question? So if we look at a classical, let's say, lattice model, 2D lattice model with all the couplings being random and time dependent,
Yeah.
and write a Hamiltonian or Lagrangian for that system and solve it. I don't know if it can be solved, or let's say some numerical thing and try to see how a wave will propagate in such a system. Something like this. I am guessing that that will be reasonably random because all the couplings with all the neighboring points are random and time dependent. And obviously this is not exactly that. This is some more generalized version, I would say. But still, I would say this kind of coupling with random and time dependence is something that can be related to that. So what I'm thinking that the randomness that I will get there and then the randomness that I'm getting there, and the difference between these two can be thought of the quantum thing that we're getting, the quantumness of the quantumness of this randomness, of this random motion. So that is what I'm trying to understand, because this setup is reasonably new for me, and I'm not
Yeah, I mean, I would say, like, if you had this, like, excitation propagating in a random time-dependent medium, you would expect it to be scattered, but also to decay. It's like it'll just decay into the background, and it'll get scrambled up. So that's kind of the first stage of this hierarchy, but then you can go longer and, like, just have increasingly more hard to detect that you ever did anything or ever had an excitation.
And those will be quantum effects.
Those are quantum effects. Yeah.
Thank you very much.
Okay, so this is very interesting and, you know, is really potentially applicable to ADS-CFT itself, but it's harder to prove. But it's a very interesting thing to think about. And since we're, you know, at the end of the day, let me just wrap up here and say the following things. So there's a million topics I didn't have time to talk about: K complexity, subsystem complexity, Pythons, late time, etc. It's all interesting, it's all cool. Maybe the lessons for me are the following. If I try to summarize everything together, gravity seems to provide a sort of simple theory of complexity or quantum computation in sort of chaotic systems. A lot of the phenomena we expect, scrambling, entanglement growth, complexity growth, are represented geometrically in the bulk in a very beautiful way. And there's a reason to think that that is a more general thing. Like if you take n equals 4 super Yang mills and dial down the coupling till it looks like a weakly coupled gauge theory, presumably all these things are still true, but it's more complicated to describe. So it's sort of suggesting that there is some gravity-like theory of chaotic systems that's more widely applicable, and that's something that would be very interesting to find. Another lesson is that writing complicated things in terms of simple pieces is very fruitful. Even though that decomposition is not unique, in fact, that may even be a bonus, it's very powerful to think of complicated things as simple parts glued together. And maybe the final lesson is that thinking computationally is useful, inspiring. So it's nice to add a subroutine to your thought process where you simulate a computer scientist. That can be very helpful for doing physics. And it's even better if you interact with them. So interactive proofs are more powerful than non-interactive proofs. And I think that's one of the lessons of this whole development is that we really ought to think about complexity at least a little bit. And it really does have something to tell us about black holes, about gravity, and about many-body systems more generally. Okay? So thanks a lot. That's it. And while I have the floor before questions, let me also thank William and Yuan, the local people who have helped out, the GGI staff. Thanks a lot. Alice, the other organizers, and all of you for coming, giving us your time and your good questions. And all the speakers, yes. Yeah, please.
Hi, thanks for that. I was wondering how important it is that the Hamiltonian is chaotic in order to get this this feature of being approximate k-design. So if I was to give you just an integrable Hamiltonian and perturb it in this time-dependent way, what would you expect to see?
Yeah, this is a very interesting question. I don't have a general answer, but it seems like there's kind of two cases. One is that this perturbation could render the whole thing chaotic. Like maybe if you take a free Fermion Hamiltonian, you add one non-free element, that's enough to generate like complete randomness. I don't actually know, but that's one possibility. Then you might expect you do get designs, but it takes much longer. If it doesn't break the integrability, you just won't get designs. So for example, if you have SYK2 here instead of SYK4, and this is a free fermion perturbation, you can show there's a lot more dark states. So you just never get close to the K-design answer, and there's all kinds of non-decaying things that come from the remaining integrability. So that's a rich question that I think deserves a lot of inquiry. We just don't know yet.
I guess I have a question. If it's related to the previous question, is it possible to have a time evolution with an integrable Hamiltonian, then at some particular time switch to a different Hamiltonian that's integrable and evolve for some time with the second Hamiltonian and get two designs? Can you switch the Hamiltonian in between integrable? Or are there arguments that say such a thing will never give you designs?
If you do it fast enough, I think so. Like if you repeat it many times. Like there are flow K models where each step of the circuit is integrable, but the combined thing is not. So that's one example. There's also a paper where people use a sort of integrable like Ising-like chain with random couplings. So it sort of maps to fermions. And they also were able to establish some design result for sort of early times, but it sort of petered out for a while because it's free. But yeah, I think this question of like what happens when this is integrable, I guess maybe the part of the point here is that I could make this arbitrarily simple, like just Pauli Z. So by itself, it won't even form a one design, let alone a K design. So all the power, so to speak, is coming from this Hamiltonian. And this is just giving me a little bit of randomness that I need kind of to make the thing work, but really the structure is coming from this thing. But yeah, what happens when they're sort of intermediate is an interesting question.
Expansion.
Yeah, so like the classic example is like this. So each of these are integrable separately, but the combination of them, in fact, if you tune them in the right way, you get some very strong kind of chaos. And if you iterate that, then it could do this.
Are there more questions? Or
Alrighty.
then I guess it's the end. Thank you very much for participating.